Hello and welcome to the absolutely simplest backpropagation example. In this video we're going to be looking at a simple neural network consisting of two nodes on two layers, the input layer and the output layer. The input I, the weight W, and the output activation A are all scalar values. There is no bias unit and there is no nonlinearity involved. The activation is simply the net input, or the input times the weight. We randomly initialize the weight to 0.8, and we have a simple training data set consisting of an input 1.5 and desired output 0.5. So with I being 1.5, we would like this network to produce the value 0.5. With the current weight, however, you can see that it actually produces 1.2. We need to define the error for the network to be able to train itself. We use the mean squared error as our cost function. So we simply take the difference between the output and the actual, the desired and the actual output, and that's squared. Looking at the activation as a function of the weight, we can see that whereas it is currently up here, in order to bring it down to where we want it to be, which is 0.5 for the activation, the weight has to be just above 0.3. Now, to formalize this desire of ours, we bring in the error function, which when plotted looks like a parabola. And you can clearly see that the minimum of this cost function is around here, which is what you would expect. Now, the backpropagation algorithm seeks to minimize the error by descending along the cost function. This is called gradient descent. It looks at the slope at each given point and figures out which way is down. So we need to know the slope, or the derivative, of the cost function, which is simple to calculate. However, the only thing we can change in the network is the weight, W. So we need an expression for the rate of change of the cost function with respect to W. And for that we need the chain rule of differentiation, which states that if there is a function of a function, the derivative of that function is the derivative of the inner function times the derivative of the outer function. This should be familiar to most of you. Alright, so what we're trying to find out is how much can we improve the situation? How much can we reduce the error by adjusting W? And we obtain this by finding out how much W affects the output activation and how much the output activation affects the error function. These two derivatives, of course, are very simple to obtain. We get the derivative of the error function with respect to A. That's very easy to get, and the activation similarly. The derivative with respect to W comes out to the input value 1.5. When we multiply those two together, we get this first order polynomial, which is plotted here, and this tells us the direction in which we need to change W. So on this side we need to deduct or reduce the W by a positive number, so we're actually going down. And on this side the gradient is negative, so we need to deduce from W a negative number. In other words, we're increasing W. That makes sense because we're always converging towards this point. From this side we go down towards this point, and from this side we go up. And that is how gradient descent works. We descend along the error function using the gradient. So now we have all the parts we need to actually learn and train the model. We are going to reduce the weight, or modify the weight, proportionately to the gradient. We also use the so-called learning rate to define by how much exactly we are going to bring the effect of the gradient into our variables. So in a simple expression, we deduct from W, the old W, 0, the rate of change of C with respect to that W times the learning rate. And in this case, we have 0.1 here as our learning rate. 4.5 times W0 minus 1.5 is our gradient. And we are ready to start calculating numbers. So as you remember, our weight was 0.8. When we put that value in here and calculate this, the value of this expression, it comes out to 0.59. And we iterate this. As you can see, we start converging towards a value, in this case 0.33333. So that's how backpropagation works. We have now trained this model, and the optimal weight for this model is 0.33. This is also very easy to generalize to several layers now that we understand how the chain rule of differentiation is used in backpropagation. So previously we looked at this part. So we have the rate of change of the error function with respect to the output activation. Then we have the rate of change of the output activation with respect to the weight immediately behind the output activation. And this was by how much we changed W. Now on the next level, backpropagating, as it's called, we use the same terms, the same coefficients here, but we add another factor, which is how much does this W change the error. And so on, we go one layer after another as far as we have to go. And this first part is always the same, so we can just carry that along as we go. Here you can also understand that it's easy to do gradient clipping. All you have to do is take this value and do a max operation with a threshold. So in more practical terms, if we look at, for example, how much we would have to change W3, so what would be the new W3 or W3 prime. So given the old W3, we would deduct from it learning rate times this expression, which comes out to these guys here. So the activation thus far, so the activation from the previous layer, times the multiple of all of the weights in front of it, and then of course the rate of change, or the difference in this case of the output activation. So in intuitive terms, what this means is the higher the activation behind this weight, the more significance this weight has for the network, and therefore we change it proportionately to the activation from the previous layer. And similarly, the weights in front, or as I would like to call it, the path from this weight all the way to the output activation, this tells us how significant this feature is for this given output. And if that path is clear, if the strength of these weights is strong, then again the strength of our adjustment, or the rate of adjustment, is also going to be great. So that's what I had today. I hope you enjoyed this video. Please comment below and ask any questions you might have. Have a great day.